Okay, welcome back from the break. We got our last two sessions of the day. They're going to both be focusing on containers, and we're going to start it off with Alberto Garcia from Do IT Now.
Hello, thank you very much. My name is Alberto Garcia. I'm a PhD in computer science and technology, and I'm a HPC architect at Do It Now. We are going to discuss here a project we have done for one of our clients, okay, about container technologies for HPC. Okay. So first of all, some words about Do It Now. Okay. We are an European society focused on delivering HPC services all over Europe, okay, and even in New Zealand. And we basically provide services for all the parts of the HPC lifecycle. Okay, we deliver services of consulting, installation, and support of HPC systems and infrastructures. Okay, we have a number of headquarters originally in France, Spain, and Italy, but now we are very, very happy to announce that we are opening in Germany. Okay. We have an office as well in New Zealand, and we will be opening very, very soon on Switzerland. Okay, so we are focusing mostly on Europe, and we can provide services all over Europe. Okay, so with that out of the way, let's discuss a little bit about the project we delivered. So basically, we were contacted last year by the CECNES. Okay, CECNES is the Centre National d'Études Spatiales, National Center for Space Studies, okay, in France. And this is a very nice institution, okay, it's a partner of the European Space Agency. They they are basically an institution for space technologies. They build satellites, they provide studies, information. Quite big, okay, it's half public, half private. And they have a very nice HPC center, okay, and with a lot of constraints and requirements of security, okay, because they deal with very sensitive data. And we were contacted by them, okay, we were contacted by them because even though they have already some skills on container technologies, they wanted to upgrade their knowledge, okay? Basically, they wanted an up-to-date state-of-the-art, okay, on container technologies that can be provided to the users to be used in their infrastructures, okay? And eventually, what a component of possibly providing a continuous integration system, okay, linked with the HPC, okay? So they want to both provide to the users containers, kind of generic request. Is up to us to recommend and to assess what kind of container technologies, and possible with a link to a continuous integration chain, okay? So what we did basically is to divide the project in three different parts, okay? The A part, we delivered a state-of-the-art, okay? We basically gathered all the information and what we consider it was during the last 2 years, the state-of-the-art in container technologies, and we provided to them, okay? We did the state-of-the-art, we choose with them one technology to provide us POC, okay? A prototype they can evaluate, and they can see if they can provide that to the users of the HPC center. And finally, the last part was the continuous integration, in which they can see how they can link their continuous integration chain that they have already won, and very, very nice, very useful, but link it to the HPC system that they have in place. Okay? So three different parts. So, okay, we went for it, and we started composing our state-of-the-art in container technologies, okay? At the moment of providing this state-of-the-art, we wanted to focus on different aspects, okay? The first and most basic aspect for delivering container technologies for the users is the functional part, okay? We need to understand what are the use cases that we are going to provide, but not only for the users, but also for the administrators, okay? What are the conditions, in which conditions we can deliver these container technologies to the users, okay? For the image administration, how the images are stored, who has access to the images, what is the format of the images, any additional requirement, like can be, for instance, a catalog of image, a closed set of services provided. For the image execution on the HPC cluster, what is the integration with maybe the workload manager, parallel file system, the type of HPC technologies that are always difficult to integrate with containers. Image creation for both the users and for the admins. And as it is very, very popular nowadays, if there is any kind of integration with maybe different paradigms, more like orchestration tools like Kubernetes, or is it compatible with a new paradigm rather than the traditional HPC workload manager, okay? We also wanted to provide this state-of-the-art from a security analysis point of view, okay? We wanted to focus on the architecture of the technology, whether it's the well-known root-owned daemon and what are the consequences for this, okay? Whether we are speaking about a tool with set-UID binaries and what are the consequences for this, whether it is allowed or not by their security department, or whether the tool runs in full and privileged mode, okay? And what are the consequences of this, because run full and privileged mode tends to have certain limitations with regard to the things that you can do with the tool, okay? It is not possible always with full and privileged mode. But we did not only focus on the architectural point of view concerning the security analysis, but also a little bit of an analysis on the code, because that can be as well very interesting in order to show what is the stability of the tool and the security of the tool. What is the number of CVEs that the tool has had during the last years that can give you a glimpse whether the tool is stable and it is well coded, okay? And what is the releases and the number of patches the tool is having, okay? That is also very important from a maintenance of the product point of view. And finally, other non-functional aspects that we included in our state-of-the-art, okay, is the interoperability of the technology, okay, whether it is compliant with the OCI models. That is very, very important for us, because more and more we see different suites, different tools on the container ecosystem that require OCI compatibility in order to work properly, and whether other aspects like support, whether there is a company behind that can provide the support, there is community activity that can serve as non-official support, and so on and so on, okay? So that was the idea of the project, okay? Provide a state-of-the-art with all this information. And finally, after the state-of-the-art, we gathered these technologies we see here, okay? We have Docker, Singularity, Obtainer, Podman, and Sarus, okay? 5 technologies. Of course, we know there are more technologies. We have NVIDIA en route, we have several Charlie Cloud, okay, all maybe not so popular nowadays container technologies, but they can fit in their niche for certain requirements. But these for us were the most interesting to evaluate, okay? Of course, we start with Docker. Docker, we think that is not appropriate for HPC due to a number of reasons. Okay, it is a root-owned daemon. You cannot give users direct access to the Docker daemon for security basically, okay? But it is the reference container tool, so I think it needs to be included in any analysis we do as baseline at least, okay? And given that it's historically the most popular tool for containers, it has to be there, let's say, okay? So it is a good reference in order to understand where we are in containers, although it is clear that for HPC it may not be the best fit, okay? Then we have Singularity, that during all these years it has been the contendant for HPC. Okay, it has been the most popular technology, container technology for HPC. Okay, it doesn't follow the root-owned daemon. Instead, it a single binary execution that it follows an fork and exec model. Okay. Singularity process is launched, and then it replaces the application, it is replaced by the user application containerized. Okay. Problem with, Singularity is very focused on HPC. It's much more fit. The security model of Singularity has some problems because it is based on a set UID binary. And that usually is not to the likes of the security responsibles on the HPC centers, okay? That doesn't mean it's not a very powerful, very useful tool, but it has some conditions, okay? And Singularity, of course, has a full rootless mode possible, okay? But there is some limitations to this full rootless mode, and it is not the way the tool is intended to be used, at least from our perspective, okay? It is not the way this tool is intended to be used, okay? The Singularity is promoted and shown as a tool to be used on his full capabilities using the C2ID model, okay? Then we have Obtainer, okay? Very interesting thing that happened in this project is that at the beginning of the project, that it was like summer 2022, we did not have any differentiation between Singularity and Obtainer, okay? There was a fork of the code, but checking the documentation of both products, you could not see what was exactly the differentiation between both of them, okay? And then I think it was on October 2022, just in the middle of the project, Obtainer released the version 1.1, okay? And with this version 1.1 of Obtainer, you could see that there clearly that there were differences between both products, okay? Most notably, the difference were on the security model, okay? And the way Obtainer is supposed to be used in contrast to Singularity. So Obtainer is supposed to be used in full rootless mode, okay? And it is the way you are supposed to use the tool, and it is the way the tool is deployed by default, whereas Singularity is supposed to be used with a set-to-ID model, okay? And that is a very old discussion whether it is better to trust on a coded set-to-ID binary or to trust in the user namespace code of the Linux kernel. Well, I think different point of views, and I think that is what it may be behind the fork of both codes, okay? Different perspectives in terms of security. But the question is that now we clearly have two products, and we can see that there are really two different products. Okay, then we have the Sarus model provided by CSCS, okay? That is a tool that is focused on HPC, okay? We can clearly see that is focused on HPC, but without losing really the OCI compatibility, okay? That is very good for us. There is a key element in Sarus that are the OCI hooks that are supposed to provide the link between the native HPC technologies, like for instance can be the network, the parallel file system, and the containerization that is basically about abstracting all this layer of complexity, okay? So the OCI hooks should bring to the container the full performance of the native HPC technologies, okay? Sarus keeps as well a set-to-ID model, and there is no root daemon, there is no use, to my knowledge, of user namespaces. And, well, it basically, Sarus provides an ecosystem, okay, in order to leverage different tools for the image capture and the download, okay? And finally, we have the last technology in which we focus on our state-of-the-art is Postman, okay? The idea of Postman is provide a full replacement for the Docker command, okay? but without a root-owned daemon. There is no daemon, no C2ID executables. It is just a 4exec model that is supposed to be running in full unprivileged mode, okay? The problem is that this kind of full unprivileged model restricts some of the things you can do with Podman. But of course, it is a very popular technology nowadays. It is more general purpose oriented rather than HPC oriented. And the thing is, well, there is a lot of power behind Podman. There is a lot of resources trying to develop more and more the tool. So it is an interesting candidate, even though it is not an HPC-focused tool, okay? And with all these technologies, we evaluated them considering the use cases we have shown before, okay? And we provided the documentation to the client, and we summarized the conclusions that we can see here, okay? So while Docker and Podman are general purpose tools, Singularity and Sarus are more focused on HPC environments, okay? And that you can feel it in the way you use them on the HPC cluster, okay? It's much easier to use Singularity, Sarus, and Obtainer in HPC rather than Docker and Podman, okay? Singularity, Sarus, they work it out of the box practically. But on the other hand, Docker and Podman are much more resourceful in terms to interoperate with different paradigms, that it can be a Kubernetes cluster, it can be more oriented towards container technologies, okay? Docker and Singularity are much more mature technologies than Podman and Sarus, okay? Although Podman is pushing a lot of resources in order to advance, but you can really feel like in terms of documentation, in terms of maturity, maybe Docker and Singularity are much more advanced than Podman and Sarus. And one important thing is that Singularity and Obtainer, they opted for developing their own ecosystem, okay? That means with regard to the OCI compatibility that they are farther than they would like. That means that it is much more difficult sometimes to interoperate with different container registry technologies or different external agents due to the fact that they do not follow the OCI. That is changing, and I know that Obtainer and Singularity both, they are trying to recover some of the lost terrain and trying to implement more and more OCI standards and features, but it is true that they are not there yet, okay? So that is a great handicap in my opinion. And from a security standpoint, Podman is the simplest and the best architecture, okay? And it is also from a non-architectural point of view, but rather about CVEs, about resources, about support. Well, Podman is a very powerful actor, okay, because it is there and it is backed by a lot of resources. Okay, so we included all these container technologies and we delivered a state of the art. And now the guys told us, okay, guys, so let's get to work. Let's deploy the POC and let's see what happens, okay, with a real practical use case. So, and because we were very interested as well in what was about to happen and what was the outcome of this, we implemented not one but 3 different technologies, okay? We tested somehow in the SecNest HPC cluster 3 different technologies. Of course, we were limited in resources as well. We do not have infinite time and people. So first we implemented Sarus technology, then we implemented Obtainer, and then with some time remaining, we implemented Podman, okay? But our most priority was to implement Sarus. So what was the idea of this POC? Well, the idea is to install the technologies in the SecNest cluster, as I said, and then try to launch a containerized application that uses MPI, okay? In this case, we use Hydro application, that is a benchmark application used by CNRS, okay, to benchmark compiler and MPI libraries. It is clear that by no means this represents a full catalog of different maybe more complex HPC applications, okay? But it was a good point of starting, okay? Of course, a more comprehensive evaluation for sure can be done, but this was a good application in order to benchmark, so that one we took. And we analyzed as well with different MPIs, okay? We wanted to check with MPI and with OpenMP. So we ran it, we installed Sarus, okay? We performed an installation of Sarus. It practically worked out of the box, and when we invested some time configuring the Sarus JSON file in order to implement the OCI hooks, okay, that can help us to improve the performance. And then we launched the application with Slurm, okay, that was the workload manager at SecNes. Well, the line here can be very long, but basically we are pulling the image from the Artifactory of the site and then launching it straight away, okay? And this is the results that we got, okay? We tested Sarus against Singularity that was already deployed on the SecNes. It was our baseline. And we tested it against a native implementation of both Intel MPI and OpenMPI, okay? We can see here that the best performance is always with the native Intel MPI, okay? And then we have both container technologies very close, okay? Very, very close. We try to leverage on the native OCI hook, okay, in order to implement Sarus with the native, in order to link Sarus with the native Intel MPI, but we did not succeed, okay? We did not succeed, or we did not get that little extra second of performance that we were expecting, okay? But still, the results, I think we were like, there is no outlier. We can see that the technologies are very, very similar, at only a little bit worse than the native implementation. Then, basically, we did the same with Aptainer, okay? We installed Aptainer as well, practically out of the box. And we did the same as well with Podman, okay? Whereas Aptainer worked straight out of the box, we had a lot of difficulties with Podman, okay? We were, to be honest, more restricted in time with Podman than we were with the others, but still it was difficult for us to make it work. And you can see that in the launching line, okay, for Podman, that is much more complex than with the others. And basically, we were not able to use Podman with the Intel MPI, so we were restricted first to the OpenMPI. A series of problems that were difficult to overcome, okay? And these were the tests that we were doing with all technologies considered, okay? In blue, you will see that is the execution time, and in green, you have the time to pull the image from the remote registry, okay? And you can see that, well, the situation is a little similar with the most performant thing is the native Intel MPI, and then all Singularity, Aptainer, Sarus are very close by. We definitely have difficulties with Podman, very, very clearly, okay? Maybe that will be worth continuing the work a little bit in order not to rush conclusions about the technology, but from an enterprise point of view where you want to deliver something to your client and the client is expecting results, well, Podman was not successful. That is clear for us. Okay, and then finally the last part of the project, that was the continuous integration, okay? So the objective of this part is to bring all the advantages of DevOps, okay, an ICI/CD chain to automatize the software deployment and testing into an HPC environment, okay? At this point, you have the choice of whether to use cluster native applications or use containerized applications. And, well, we wanted to evaluate more or less both things, okay? Whether it is worth using native applications in which you have to compile the application directly on the HPC cluster in order to leverage the native HPC compilers You have to upload then the binaries to the remote registry because you want to conduct CI/CD stages of the pipeline, which mean maybe a scan of the binary, code analysis, and so on. Or maybe you want to go for the container side, okay, in which you build the image, you take maybe a recipe file from GitLab, you build the image, you push it, you perform the code analysis, the binaries, and then you run it on the HPC cluster, okay? One conclusion that we got here is that you can do either of them, but it is not a good policy to mix these kind of applications. It is always difficult. So one of the things that we always recommend to our clients is that either you go full containerized and you avoid dependencies with the native software stack in the HPC cluster, or you go with the native applications, but then try not to containerize, okay? You have both paths, both have different advantages and inconveniences, but it is not worth mixing them, in my opinion, okay, in our opinion, because you are going to get the worst of both worlds, okay? So whatever is your choice, stick to one of them. So the idea was to actually perform an integration with the Seknes software factory. That was a very nice, very powerful system they had in place. They have a GitLab for version control, GitLab CI for continuous integration, and they have a set of queues for security analysis of the code deployed, okay? SonarQube for the code analysis, Artifactory for managing the binaries and the images, and X-Ray for checking vulnerabilities or hidden surprises on the binaries. So we went on and we implemented this in a GitLab CI/CD chain, okay, that we can see here. We basically included, thanks to a tool called Kaniko, we implemented a stage to build the containers, okay? The users are supposed to upload to their GitLab the recipe files they want to run. Thanks to Kaniko, we build those images directly using Docker on Docker. We also compile the applications, or the user may also compile the applications. Then, if it is necessary to move from one image format to another, we include as well a task on the CI/CD. In order to do this, we move from Docker images, OCI format images to Singularity Obtainer. And then we run all the tests in the supercomputer, okay, whether they are native or each one of the different technologies. And we finally include a clean step to clean up a little bit. At this chain that we have here, supposedly we should add all the stages of the CI/CD related to SonarQube, X-Ray, in order to perform a full analysis of the code. And if you include everything, you have a very nice, very powerful CI/CD that can automatize a lot the software development on an HPC cluster. Okay, so it is a very, very interesting solution and very powerful. So in order to take the build and the execution of the CI/CD chain in the HPC cluster, we deployed one GitLab runner in one of the front-end nodes. Okay, that was kind of easy, and it can be even done by the users without any privilege at the HPC cluster level. And in order to control the jobs in the supercomputer, we submit with a slurm using the -w flag. Okay, that basically blocks the CI/CD until the job is treated by the queue system. And this is something that I already mentioned. This is the image building with Kaniko that is very useful if you want to let the users, not let the users, but build the image of the users in your own Docker container. You can have as well Kaniko implemented in a Kubernetes cluster. And, well, that allows you to be totally independent from external infrastructures. So the conclusions, okay, once we have implemented all three parts of the project, We see that there is no single technology, okay, that covers all use cases. All of them have some advantages over the others, and it is really a race, okay? It is very complicated to choose one technology as a general case. You really need to see what are the needs of each one of the constraints present, and then maybe assess what is the technology that suits better, okay? For SECNES people, we recommended Sarus for the short term, okay, because Sarus was focused on HPC technologies. It was working very well. It was a good performance, and it was OCI integrated, okay? So we could easily integrate Sarus with the CI/CD chain of SECNES. For maybe a long-term version, well, Obtainer, it seems to be, at this moment, the most active actor on HPC, okay? They have a strong community support, they have commercial product, they are using in their code sources that they are having more activity than maybe Singularity. So they seem to be very powerful. The problem with Obtainer is the OCI compatibility, but they are also working on that. So for the long term, it may be better Obtainer, but for the short term, we recommended Sarus. It is very important when we speak of kernel of container technologies to analyze what is the target kernel, because the latest kernel features can make a world of difference. Okay, they can represent the difference between the technology works or the technology doesn't work. Okay? Either we can deploy it or it is not possible, and we need to update the kernel. And finally, well, it is a landscape that is continuously evolving, so these are our conclusions for now, but maybe in 6 months it will be something different. It is really very interesting moment, and it is something that we have to follow up very closely, because every 6 months there can be a new situation. And that's it. Thank you very much. Pam pam tagadam 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 pam pam tagadam tagadam pam 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 pam